So today we're going to spend a little bit of time talking about that thing that everybody talks about but never really does, which is machine learning model deployment and production. And we're going to cover the strategy component of things as well as some implementation. So we'll get into the technical details a bit towards the end and show some examples of how we think that we can do this in an efficient, scalable way. But before that, it's probably important to do some introductions. You want to know who we are. So myself, you want to click the next slide? There we go. I'm Justin Norman. I head up Cloudera's Fast Forward Labs organization, which is a machine learning research and consulting group that has recently acquired into Cloudera. I've spent a lot of time in my career on both the engineering side and also in the data science side, so developing both scalable machine learning applications and also doing the research work behind them. So I've got a pretty good understanding of some of the things that can go wrong, and I spend a lot of my time today trying to break things that people like Sagar develop, which is great for everybody. And on the offline side of things, I really like technology of all types, so you might see me tweeting or blogging about Raspberry Pi implementations and building out mirrors that have smart features and things like that. So that's who I am. Sagar, do you want to introduce yourself?
Sure, absolutely. So, hola. I'm a strategic solution architect with Cloudera. Along with Cloudera, I've worked with multiple customers in different domains. I've worked in healthcare, finance, manufacturing, and retail industry a lot. I've worked with a lot of machine learning and data science focused use cases throughout my journey at Cloudera. I'm very passionate about speaking at public places. I usually speak at big data conferences like here, and also I do speak a lot at local meetups. I'm also a big fan of science fiction movies. How many of you have seen the recent Avengers Endgame trailer? Oh, pretty much like 30–40% of it. So the Avengers actually try to save the world. We are here actually trying to improve the world by using machine learning. So let's take a look at it, how we can improve our current world with machine learning.
Well, which Avenger are you?
I'll let you know at the end. So machine learning is everywhere. As I said, machine learning is everywhere. Probably at this point of time, almost dozens of machine learning algorithms are running in your cell phone. I'm not sure how many of you know it, but yeah, there are dozens of machine learning algorithms running in your mobile phone at this point of time. Think about Google. When you use Google, Google can tell you how you can reach in how much amount of time to the airport from this point of time. So if you want to go to airport tomorrow, Google can tell you now how much amount of time you will need. Let's think about this particular use case. There is a point A and there is a point B. You want to go from point A to point B and there is a route. And Google helps you to figure out that route. Can you figure out that route without Google? Obviously, yes. We can always figure out the route without Google by using the traditional paper maps, right? But Google is actually sitting on a mountain of data. So now Google can also tell you how much time you will need to go from point A to point B. That's the power of machine learning. Google helps you to predict that kind of amount of time which we as a normal human being can't do it. Let's think about another use case. Let's talk about iPhones. iPhones are very popular back in the US. So Apple has invented a technology where the streams of photons of your face can stream into your front-facing camera and match it with your face pattern and identify whether it really matches or not. So that's another pretty cool use case of machine learning. So as I said, we can see machine learning everywhere around us. When Google and Apple actually started on this journey, they never thought they are going to create any machine learning or artificial intelligence tools. But they iterated over this so many times that it created an entire new industry. So let's look into it more deeply.
Cool. So throughout our research, I mentioned that we do research not only on the probabilistic side, but also on the process and the strategy of how to be effective in machine learning. And we've learned that this slide, although it's simple, is a pretty good and accurate representation of what it takes to go from the journey of just collecting information all the way through automation and AI. And interestingly enough, if you've been in a big data company or built a lot of really robust big data platforms, you're ahead of the curve because we need to start with first getting all the information in one place, and that's history, right? So understanding what happened is the question that we're trying to answer at that space. If you put that another way, think of being a retailer of shoes, you can ask, how many shoes did we ship last quarter as a historical view? And those sorts of things are occupied in both the big data space for ingestion and storage and the analytics space for counting or understanding how many of those things occurred. But when you want to ask the question of how many will we ship in a future quarter or some period in the future, you cross that boundary into the probabilistic space. And that is actually really important because it's that ability to master the probabilistic space or the future predictions that are going to power this AI revolution going into the future for businesses. And what we found for a lot of our customers that are really looking to grow there is that there's quite a bit of investment needed, not just in the data platform, but also to understand what types of information that you are bringing into machine learning models, and understanding the space in which you're doing processing. So think about it this way: if you want to answer that question, not only do you have to know on a continuous scale what the range should be, but also there are a number of factors that could influence that are different than just price. Things like weather. Elections could impact it. The ability for you to ship during specific windows of trading times. All those sorts of things lead to an incredibly dynamic and highly dimensional space that needed to be considered in the process of machine learning. So it's not something that humans are particularly good at keeping all in their heads. So that's why we need machines and we need the tools associated with them in order to help us be successful. So how do we get there? So unlike the Avengers, you can't go lone wolf it like Iron Man, right? Machine learning is a team sport, and it always has been. But it's actually not just one activity. It's a number of different activities that are chained in a pipeline, or a workflow, as we like to call it, towards a specific end. And so the model development lifecycle, that starts all the way over on the left-hand side with getting the inputs and building out a robust data lake, also moves into things like the probabilistic space when you're training a model and building a model out. Keeping track of all the different experiments that you run and being able to do that in a really rapid way to test out all the different types of outcomes you could have on the way to selecting a primary model or primary outcome that you want to use on real data. Then finally, productionizing that or deploying that at scale over hundreds or maybe thousands of different distributed machines is a really complex problem when you unpack all the different techniques and tools required to implement that. So we like to centralize on a definition that we're going to use as a working model for the rest of this talk. And so that's ML in production is the tooling, technology, and best practices that are associated with taking predictive models once they're already trained into production, and that includes the hardening, packaging, deployment, monitoring, and lifecycle management for thousands of models all the way deployed at scale. So we'll work with that.
As Justin just educated us that machine learning is a team sport, let's look into the different teams and skills involved into an end-to-end machine learning workflow. For an end-to-end machine learning workflow, we need data engineers who can do data preparation for you, who can do data engineering for you, who can do some data discovery for you. You also need data scientists who can do prototyping, who can do experimentations, all those type of stuff. But we should not forget our DevOps team. They are the ones who actually build, package, and deploy a model into production. So you basically need an army of people with data engineering to ingest data into your models, data scientists to build your models, and DevOps team to actually deploy those models. And all these different teams do not speak the same language. Also, on the similar lines, they have their own skill sets, own tools which they use. Like data engineering mainly concentrates on data, Hadoop, big data platforms like Hive, Flume, Kafka, NiFi for data ingestion, while our data scientist teams are more. Sorry?
Don't forget SQL.
No, not at all. Yeah, SQL is the core of the complete ecosystem, right? Data scientists, they are much more fluent with Python, Scikit, TensorFlow, etc. While our DevOps teams likes to play with Kubernetes, Docker, some resource managers like Yarn and Mesos, also some testing tools like Jenkins, etc. So we need a range of skills, range of tools to be successful in a big data ecosystem. As per my knowledge, I don't know any tool which has all these skills or functionalities available at a click of button. So basically, one of the challenge which we have as part of the ecosystem is to solve this tools problem.
Thanks, Sagar. So another one of the challenges that we run into is defining what a model actually is. And I would love to say that this is a simple answer, but the reality is there are as many definitions of models as there probably are data scientists out there, and that's growing, we know how rapidly, every day. And the reality is that we try to abstract this down to thinking of a model as really just a collection of code. Really, it could be written in any language that represents an algorithm that's designed to, given an input, produce or provide a prediction. And that code can take a lot of different forms. It could be R scripts, Python code. It could be actually even encapsulated into some kind of virtualized image. And it really doesn't that matter as much. But maintaining these models over a large scale that we mentioned before can be quite difficult. So a few models is not that hard, right? You could just wrap it around even a cron script and then just run it and then manage it when it goes down. You're the data scientist that put it in place, so you know what to do. But when you add that to 50 models, 100 models, 50,000 models, like some of our oil and gas customers have running in production, it's obviously impossible to manage that via simple command line scripts and as an individual human. So we start to need these same sorts of continuous improvement and integration tools that were available and already available in the software engineering lifecycle, but we need those to be robust for the flexibility and experimentation required by data scientists. And to be clear, I'm actually shying away from talking about specific formats. So I'm sure many of you have heard of things like PMML, ONNX, or TensorFlow serving, MLflow models. These are all representations of a convention, and that's all well and fine. And honestly, some of those are going to be great for a particular application. But the challenge is not so much in a definition or a convention. That's a thing I think that we can all come to for our individual architectures. It's really making the system robust to the portability and compatibility that you need to have to both collaborate internally with your data science teams and also to be able to rapidly scale promoting and demoting models in production. And that is something that none of those individual formats have solved from the ground up, just like Sagar has said. And if you haven't read this paper, then I highly recommend that you do so afterwards. This is Google's Hidden Technical Debt in Machine Learning. And it goes through a lot of the issues that really come up around doing machine learning, not just in production, but in general, and how it becomes a software engineering problem that really scales and gets worse and worse and compounds as you go through the development cycle. But what I want to highlight here is that in the middle there, you see this tiny little dot, and that's the machine learning code. So it's meant to tell you that in a production, sometimes it's less than 10% of the lines of code that are written in a production ML system are related to the machine learning function itself. And that's not to say that machine learning is unimportant. I'm a data scientist, so it's the most important thing. but what I am saying is that at the end of the day, when you're actually solving a problem for your customers, for your users, that code that's actually providing the decision function is almost irrelevant from a time a pure coding perspective. And so all these other things that you need to do, all these other systems, capabilities, all these other architectures and tools are going to be a part of making the workflow a reality for production use. And so spending some time up front designing that architecture and making sure that it's invested in is really important to do, not just spending the time solving the machine learning problem.
As Justin mentioned, that machine learning code is just a fraction of a machine learning workflow. So let's take a deeper look into a machine learning workflow or a traditional data science workflow. So basically, you have a data stored, your raw data stored in some storage format. You do some data engineering, data prep on that data, then do some feature selections, do some experimentation, train that model, and deploy on your infrastructure. That's so easy. That's so simple and straightforward. I don't know why Justin is complicating this much things. It's very simple and straightforward. Let's go for a drink now. But it's actually not. When we try to combine all these phases together and make them work in like a production ML kind of a situation, it actually arises a lot of complexities. So let's take a deeper look into those complexities. Wow, the same diagram, but with complexities. On this diagram, I mainly see a few challenges, and let me take you through some of those challenges. The very first and the foremost challenge we see is the tools. We have variety of tools for each of the different phases in a machine learning workflow. We have separate set of tools for data engineering. Each engineer likes their own set of tools. Similarly, we have separate set of tools for machine learning and experimentation, where each data scientist loves to train and use different algorithms and framework for their work. Similarly, we have plenty of options for deployment. So tools is one of the main issue or challenge which we are seeing in an environment. Also, unlike other software development cycles, we usually, like in our enterprises, we pick up one application and we use it across the enterprises. But machine learning doesn't work in the same way. If you need to have access to different type of algos, different type of frameworks like TensorFlow, XGBoost, MLlib, etc., so that you can test your data set based on different use cases or business problems you're trying to solve. So it's not the traditional software development cycle which we see. The second issue which I want to focus on is experimentation. Whenever you test your models and whenever you tweak your models with any code changes or any hyperparameter tuning, all those kind of stuff, we need some ways to track that information. We need some ways to do bookkeeping about it, like what changes went into it, what framework did we use, what parameters did we tweak. So we need to keep all those parameters tracked somewhere so that it's easy to look at the history, like whether we are improving the accuracy or we are going in the other way direction. So we need ways to do that bookkeeping. Apart from that, I also want to talk about the scale issue. Whenever you deal with more data and your data keeps increasing, you always want to make that whole data available for your training. So as soon as your data increases, it becomes very complicated to pre-process your data because your data is now much more in volume, to train your data because now you need much more compute to train with that particular data set. So scale is another issue. And also whenever you deploy a model, you need to think about scale over there as well, because the more people are hitting to that model and the more people are consuming that model, you need to ensure about high availability and all those kind of things. So scale is the third thing which I want to consider. And the fourth and the most important thing is integration. We are seeing different phases here, different tools here. How these different tools are going to talk to each other, how you are going to integrate all of them together so that you can get a end-to-end machine learning workflow working successfully. Not last but not the least is we should not forget about security. We should not forget about governance. Like when you're moving the data through all these phases, you don't want to create different data silos because that's another pain point which we see in the enterprises. So you have to think about all those challenges when you're going through a machine learning workflow.
Sure. So Sagar and I actually do a lot of work in the field, so supporting our customers. And we hear a lot of feedback about how they've actually built a data lake. And they've standardized the data engineering, data ingestion, and security data set, and put some governance, just like we talked about around it. So just as a poll, how many people have deployed a data lake inside their own environment? It should be, hopefully, a lot of people at this point. Wow. Cool.
Smart guys.
Yeah, exactly. Yeah. And so how many of that same group have a clear workflow from taking your data from that data lake and then building machine learning applications on top of it and tearing it all the way through to production? It's a much smaller group of people. And there's some challenges around that. And so let's talk about that. One of the biggest things that comes into play is that we're actually talking about completely different skill sets and also completely different outputs. And what I mean by that is we like to think of this as like the recipe versus baking a cake perspective. Data scientists like to do their work in experimentation environments, like things like Jupyter Notebook or IDEs. And so what you get from that is essentially a specification of how to do a thing. But it is not the thing in and of itself. It's not the actual output. And so you get a recipe. And then the workflow that we love to do is just say, hey, here's a recipe. Machine learning engineer or data engineer, go bake that for me and then serve it to my users. And I'm going to go back and do some more baking and recipe creation. And I'll come back to you later. And that doesn't work out very well because the machine learning engineers actually weren't there for understanding what should go into it, the ingredients, what the proportion is. And they start to take their own jazz with it and make something completely different. And then when you get to production, the thing that was originally specified by the recipe ends up not necessarily being useful or even working at all in production. And so what we try to do when building out an enterprise machine learning platform or when you make these decisions is to A, physically keep them closer together so that they are having the development process themselves, but B, to make sure that there's collaboration embedded in the system so that the development process is not isolated. And that's from a code perspective and also from a workflow perspective. So just to kind of summarize some of the challenges that we've talked about here in just a bit, it comes down to basically access to scale in the developer experience. On the access side of things, Sagar already mentioned that we want to make sure we have flexibility and different capabilities around the tools, so you want to be able to use whichever libraries you want, and then also security built into it, so things like role-based access control are really important. On the scale side, having parallelism or having the ability to leverage code that's specifically written to take advantage of distributed compute or GPUs is something that, of course, needs to be built into the workflow. But as a data scientist, the thing I'm most passionate about, and I will talk to from experience, is that if the developer experience or the data science experimentation experience isn't robust and it isn't easy to use, we'll probably just download something from the internet and start doing it on our laptops, and then we're back into that recipe conversation again versus cake conversation again. So you want to make sure that whatever you build, you're not creating an environment that's really CLI first or tools first, but actually is robust for the experience that a data scientist or a group of data scientists want to have while building out the machine learning capability. That way, you get to take advantage of all the things that are happening from a scale, compatibility, and governance perspective, but you don't have to worry about people building things under their desk like I used to do. And the good news is you've got options about how to actually implement this. So we'll shift into talking about what we can do. And the bad news is that you've got options. All right, next slide, please. So to kind of frame the conversation about what we think is sort of best practices here, we have to kind of start with looking at some of the people who have led the development of the capability. So these are folks like Uber, Netflix, Airbnb, Facebook, who've built entire machine learning platforms from the ground up all the way in. So they're ingesting data at literally at the edge for their consumers, and then they're building machine learning capabilities that they can rapidly experiment with and deploy at a moment's notice. This is great. And honestly, if you have the ability to be able to do that, then I say go for it. But let me tell you a little bit about what that took. Millions of dollars, hundreds of people, and quite frankly, years. They're still building them. So if you're not in that position, then we're going to have to figure out how to put together the open source ecosystem that exists, as well as the commodity ecosystem that exists, to build something that's robust. And so it comes down to a few bottom line principles. First of all, enterprise machine learning requires looking at the big picture. So it's not just the big picture in terms of the model or in terms of the problem space, that those are important, but the big picture from a data engineering and data platform perspective. You have to build out the extensions to your data platform, into your workflows for data pipeline that include machine learning as an output, as an end in of itself. It has to fit within that broader ecosystem. Otherwise, you're going to be stuck with point solutions that are going to solve for a particular part of the machine learning workflow, for example, the editor experience, or for example, things like automatic parameter tuning. But they won't solve for the entire challenge, and you'll get to a point in which you'll have to be doing that in a custom or semi-commoditized way. And if you're doing that at the point of a production workflow, if you're waiting until you're actually trying to get it deployed, that's critical months, or critical even years, to getting that into production. And that can be the difference between being competitive or not with a machine learning capability.
Model development. Many times, like when we are working on the model development, you have variety of tools which you can work on. Like you have tools got Jupyter, PyCharm, etc., where you can develop your tools and ship it to the DevOps team to package it and rebuild it. So this is the problem which Justin actually spoke about. Like you are building your models as part of your notebook environment, and then the DevOps team actually have to recode it so that it is in a deployable version. Also, a lot of tools don't give you capabilities of elastic compute and all those things. So we have to think about those aspects as well. Justin, do you want to add anything on this?
Yeah, so the only thing I would say on this slide that is really important, and it's underlined at the bottom, is that any tool that you choose, and there's a lot of options, should not make you move the data into the tool in order to be able to use it. And I can give you a more concrete example of that. If you have to upload your data into some cloud service, and then reprocess it again in that cloud service, and then actually do your machine learning, and then ship it back into whatever the production environment it is, that's probably not the best development experience. And there are a lot of point solutions out there that are available for purchase that want you to do that. And it makes a lot of sense for them from a financial perspective, but actually makes it much more difficult on the scale and production side to get to the answer.
Let's go into training and experiment. So Justin gave us a little bit of overview about model development, but we also need to find out ways where we can actually experiment and train our models. So in the traditional ecosystem, whenever we build a model, a data scientist always has a curiosity in his mind, whether the best model he has built is really the best model, or there exists any other model which can perform even better with different algorithms, with different frameworks, or maybe with different data sets. So that question always exists. This question is very similar to some of the legacy website designing world, Where in website designing world, always there used to be a curiosity whether this website will get more traffic versus this particular website. So they came up with a way of called as A/B testing or something, where they will host both the websites parallelly and see which website is getting more click rate and all those things. I think we need similar kind of capability with our model deployments as well. We should be able to parallelly evaluate how our models are performing, which model is giving better accuracy, which model is having better root mean square error, mean absolute error, all those different type of parameters which you want to track for at a model level. You should be able to parallelly track those. And apart from that, I discussed one of the other thing is bookkeeping. We need to ensure we are tracking who has deployed this model, what tweaks he has made to this model, what parameters he used for this particular type of accuracy to be achieved. So you need some kind of bookkeeping way to also track all this information. So if I think at a very high level, I need some ways to track the version of my code because my code is changing, and I also need to track the artifacts related to the code. So when my version is changing, what exactly I'm changing? So that kind of bookkeeping information. So I'm looking for that kind of capability to solve my experimentation issues and training issues which I see in the real world. There are some tools, proprietary tools, and some open source tools which actually solves this problem. So one of them which I have personally used is DataMo, where you actually can track experiments for your models. But one thing I would like to emphasize here is when you're introducing this kind of tools to solve a particular problem, you're actually creating a bigger problem. The thing is you're introducing more and more tools in your ecosystem, and the more and more tools you have in your ecosystem, it becomes difficult to maintain security, governance, and data flow across your ecosystem. So you have to be very careful when you're introducing more and more tools to solve these small problems, but on the back end, you're actually introducing some bigger problems which are very difficult to solve. Model deployment. This is another very interesting factor, and model deployment patterns is mainly driven by the use cases. So based on the business problem or the use case we are trying to solve, there are commonly few model deployment patterns. This is not a comprehensive list of model deployment patterns, but it covers most of the commonly seen deployment patterns which we see on the field. I can mainly categorize these model deployment patterns into three main types. One is the batch model, which is very traditional, has existed for a while now. You can mainly these models are used for like daily scoring or a weekly scoring, and some of the examples of the use cases are email campaigns or maybe banking transactions, all those kind of stuff. The another type of model deployment pattern is real time. Yeah, everyone likes real time. Everyone wants their data in real time and wants analytics in real time. So there are mainly two type of real-time models which we see in the field. One is like front-end type of real-time models and back-end type of real-time scoring models. When I talk about front-end real-time scoring models, you would be pretty familiar. Like when you go to Amazon site or Netflix site, you see a lot of recommendations coming out. Those are very good examples of a front-end type of models. While in terms of back-end type of models, think about when you swipe a credit card or debit card at an ATM. They try to identify whether it's a fraud or non-fraud. It happens in real time and authenticates or disapproves your transaction. So those kind of a back-end type of real-time models, which you are not seeing, but they're working behind the scenes. And the third and one of the very exciting type of model deployment pattern, which is gaining a lot of traction in the field, is scoring at the edge. Now this model type has got a lot of traction because of the autonomous driving, which is coming. Like a lot of big players are testing that thing, and also like predictive maintenance. In this kind of use cases, it is very difficult to transfer a lot of data back to the data center, do the processing, and send back the analytics to the edge again. So what these models are doing, they are actually doing analytics and scoring at the edge itself and deciding whether it's something which should go forward or just stop over there. So those are some of the commonly type of model deployment patterns we see on the field.
And so just really quickly on this slide, from a data science perspective, this is where the decision around which language you use and which library set you use becomes extremely important. On the batch side of things, I think we're all familiar with using Python or Scala or Spark to be able to perform a somewhat batch-oriented or non-time bounded deployment. But on the real-time side of things, things get a bit more interesting. From a low latency perspective, There are obviously tools that allow, like NiFi and Kafka, that allow you to handle real-time streams and low latency. But when you need to provide a function that's not even at the edge, but really quickly, this is where rewrites are really common. So like going down into C or into a lower level language that has more of an architectural play, and can take advantage of parallelism is something that happens. So being aware of that at the beginning of your development cycle and what the actual use case looks like for your users is really important.
And this particular slide talks about the deployment format. So we spoke about the patterns. We also need to shed a little bit light on the deployment formats as well. PML, I'm actually going to take like anti-clockwise direction to cover this slide. So the PMML format, like it's a very traditional format, has been there for a while now. It's mainly used for like predictive kind of machine learning algorithms, and it's mainly Java focused. It doesn't get benefits of all the Python world and all the innovation frameworks, tools existing in Python. So it's like a Java focus, and it has been there for a while, but a lot of new innovation, and it's not getting benefited from the new innovation happening in the Python side. While we have seen like a lot of Java, C++ type of model formats also in the field. Like some of the big banks, they are using some like a high frequency trading model, which are actually built on in C++ format and deployed in like C++ format, and they are performing really good. But again, those models has been there for a while. It's very difficult to create new of them because a lot of support is not available for those models, but they are occupying some part of the market. Another type of model format which we see is like building your whole model in Python stack. Again, like this particular model gets edge of all the innovation and new things which are happening in the Python world, but whenever you try to package a Python application, you have to include all the dependencies. So it becomes quite big and clunky to manage those kind of models. And the last is like API-driven models. This is where most of the big players are actually investing a lot to improve this kind of model, because this model actually provides a lot of benefits compared to all three of them. It is like very agile. Like you can make changes very quickly and deploy the new API without even like the customer noticing it or the endpoint noticing it. Similarly, it's very scalable. Like you can always do fault tolerance and all those kind of things with an API-driven kind of model. And also they are very fast. And one other thing which we spoke earlier about the challenges was integration. Think about it, like how API can help you to integrate your whole ecosystem. If your model is deployed as an API, you just have to call that API within your application. So basically everything is modularized. You can keep your model changing those APIs, the API endpoint will remain the same. Similarly, you can keep changing your applications and your API is not impacted. So it's like a modular approach which API-driven model helps you to achieve. And I just want to add one more thing here is like with the inception of tools like Dockers and Flask, all those things, they help you to spin up Dockers in like quick few seconds and help you to create like a Flask API REST endpoint so that it can serve your model. So it has been one of the areas where a lot of new inventions has been happening.
Cool. So we're going to move pretty quickly through this because I do want to show you a little bit of some of the work we've been doing at Fast Forward around this. But model monitoring and instrumentation for performance measurement is extremely important. And so we've talked now about the entire workflow or entire life cycle all the way through being able to have your model up and serving its users or serving its purpose. But as everybody knows, models do not age like fine wine. They get worse immediately once they're deployed. And so understanding how how that model drift occurs, whether it be from a statistical perspective, so things like the error, the accuracy, and understanding its effectiveness under the curve, things like that, or from a performance perspective, is it actually meeting the service level agreement from a response time perspective, or is it consuming the appropriate amount of memory over time, are both different dimensions that need to be captured, also saved, and analyzed over time. So the good news is for software engineering, and analytics applications, we've been doing this for many years. Instrumenting that into the machine learning workflow is definitely not the default position for machine learning developers or for data scientists. So this is something that, from a data platform perspective, some of you who are on the engineering side can really help us be successful with. But the reality is it has to occur at the beginning of the production workflow, and the design is just as important as the implementation. So from a Cloudera perspective, just to bring it all together, we have a pretty specific view on how best to do this, and that's the way we've orchestrated machine learning at our company. First is to provide a platform which creates all those data platform capabilities that we've just talked about before. Then to build an integrated data science development environment. So that's the Cloudera Data Science Workbench. And this allows for that collaborative, scalable design and development that we've spoken about so much. And then finally, we have the organization that I'm a part of called Fast Forward Labs, which provides expert guidance and use case refinement and technique support to be able to build scalable machine learning apps on top of the stack.
Wow, the Lego movie. How many of you like Legos? Wow, a lot of them, yeah. So the most important thing about Legos is they come in pieces. So let's try in a fun way, whatever problems we have talked about, let's try to put Legos for the solutions which can help us to try to solve those problems.
We may need to go fast on this one.
Yep. It's very fast.
Yeah.
Okay. So these are different Legos which I was talking about. So basically, we need some kind of environment where we can host our packages and dependencies in an isolated environment, because a lot of machine learning happens with specific libraries and specific versions. So you need to containerize all those things into something called as containers. And one of the popular tools for those kind of offerings is Docker. When you deal with Docker, you need a way to deal or manage those containers. So we need some kind of orchestration layer like Kubernetes. We need some of the important capabilities like sessions management and job management. So when I say session management, is like if there is an admin who wants to manage and see how much resources are being used in the environment, we need some way to find that information. Similarly, if you want to schedule some ad hoc job which you want to run on a periodic basis, you need some ways to schedule jobs and all for our data engineers or data scientists. We also spoke a lot about experimentation, like how to experiment data along with tracking the bookkeeping information. To do that kind of functionality, you need multiple versions of the code. And when you want to deal with multiple versions, maybe you need multiple images of your Docker image. So that's why I'm showing here like multiple Docker images on the right-hand side. And you also will need a model REST API endpoint so that you can serve your model in an agile and scalable way. So this is kind of a Lego block of the solution which can actually help us to solve some of the challenges which we have discussed. Now, these are a lot of things to be actually packaged in an environment. So I don't know who can actually save us here to solve all these problems. So let me tap to my friend Justin to see if he has any solution for us.
Sure, of course I do. So I mentioned before that we do quite a bit of research and development at Cloudera to try to understand how to solve problems like this. We believe that the answer is not so much around the best or fastest machine learning models. I mean, someone is going to solve that, and that's great. We'll all benefit. It'll be open sourced. But it's the actual industrialization of the enterprise ML model that's really important. It's all those things in between, those things that surrounded our 10% of ML code on that slide that I showed earlier. And so over the next year, we're really focused on building out and building on top of our software platform and also tools like Cloudera Data Science Workbench to be able to solve for exactly the types of challenges that we've talked about in the pattern that Sagar just described. And to kind of demonstrate that, I'm going to show just a quick workflow of machine learning deployed. And it's in the context of some of the work that we did in Cloudera Fast Forward Labs from a research perspective. For those of you that are not familiar, we actually released a report about 4 months ago on federated machine learning. So federated machine learning in a nutshell is being able to conduct machine learning at the edge, but keeping privacy and data management as a forefront of a capability set. And making that much simpler is essentially training a model on a node or at edge, like think of it like a phone, and then being able to ship that model back to a centralized server and maybe do that 500, 50,000, 100,000 times, receive a much higher aggregate or generalizable model in the server without shipping any of the data back and forth to accomplish that. And the way you accomplish this is very simple. It's actually transporting the model itself, so the weights or the hyperparameters, instead of the data, and then performing federated averaging, a process of bringing together those model weights on the server and then putting that back down at each one of the edge nodes. So we created a simulation of this called Turbofan Tycoon, which is one of the prototypes that we launched, which is based on the CMAPS data set. So if anybody's done predictive maintenance, you are very familiar with this data set. It's like ImageNet for that space. And we created a simulation where we showed a set of models being deployed at the edge for each one of these turbofans, and then converging together to come up with sort of the Uber model, and then that convergence process resulting in the best version of the model being deployed at each one of the nodes. So I tell you this backstory to show you that we did this all on a single machine, so it was a simulation, but we utilized recently, for the purposes of this demo, CDSW to break that out. So now we actually have real federated nodes, so my laptop's going to act as the federated node, and then a server environment where that averaging is occurring, and that's being done through Cloudera Data Science Workbench. So I'm going to show you that really quickly, and to help illustrate how the Data Science Workbench product helped us, Sagar's going to narrate.
Perfect. Thank you, Justin, for sharing us some solution to all our problems. So this looks like the login screen to the CDSW tool, which Justin just introduced us. On the front screen, we can see there is a session resource management. So you can see like how many sessions are running, jobs are running, how much CPU and memory are being utilized. So pretty good overview about the resources being utilized. On the right-hand top-hand corner, I see Justin's name over there. Looks like it's some kind of context management. So looks like we can actually work between multiple teams, do access management from this particular portlet. And in the middle, we can see the projects portal. So let's go into the, let's see what Justin has been doing for a long time now. So within this particular project, we are seeing like there are some files on the top, on the left-hand side, we see some models, experiment jobs, and on the right-hand side, we see open workbench. Let's go and click the workbench. Let's see what happens. Okay, when we click the workbench, on the left-hand side, we see all the files which are part of the project. So you can always look at the files. Then in the middle screen is more about the code. So whatever files is selected on the left, that particular code is visible in the middle, which is like an editor kind of tab. And on the right-hand side, it gives you information to spin up a particular Docker session. And this Docker session is independent of the different languages. Like you can spin Python 2, Python 3. So it looks like it's like kind of a language agnostic. And at the end, we can also see the resource management information. So you can spin based on the resources you want to give to your container. And in the middle editor tab, that's where I think what Justin was talking about, like federated averaging code, where you actually ship your models and get the weights and do the averaging. So all that information is in the middle part. Justin, why don't we deploy this model and look at the model deployment?
Sure. So I've already deployed it, so we didn't have to worry about that.
Great. So looks like Justin has deployed a lot of versions. So you can see that like he's
a process.
on 186.
It's experimentation. That doesn't always work.
I think you do a lot of work. Good. So yeah, looks like he has deployed a lot of versions. He has built versions. So someone is keeping that housekeeping, bookkeeping stuff for us. So someone is tracking all that information which we are looking at. We can, in the status, we can see some models are in deployed state, some are in stop state. So it looks like we have capability to deploy the models parallelly. Justin, can we go in the build section?
Sure.
So build tab actually gives you information about building your models, and at the bottom we can see logs, all the logs about that model which is being built. And if we can go into monitoring.
Sure, let me go ahead and run it.
Sure.
Cool. Yeah, so monitoring, this is the last bit that we were talking about before, about having instrumentation appropriately. And not just understanding how your model runs once, but how it runs over a long period of time, and having an error handling, and exception handling. So you can see here that at the top level, we've got the number of actual process API calls, whether or not they were successes or failures, and how many times that it was busy. So one of the things that can occur is if you can have too many requests occurring at a single time for the system to handle, and that is one of the performance functions that you have to manage. That's different than just running on your laptop. What I'm doing here is, like I mentioned before, I have my laptop acting as one of the worker nodes. So it is running 80 different segments of the data, and it's running individual models on those 80 different segments and converging towards a federated model that is the best for all of them. And so what you're actually seeing in the console output down here, or the error log output down here, is each one of the instrumentations that I've put into the code. So it's about in action of just pushing the model itself. So this is the update function coming from the server, a pull from the server on the model side, and then the train function for each one of them, which is that model being trained and then converging on the best side. So you're not just getting some instrumentation around how the model's output is. The loss function is in here, and that's great. But it's about how the model is performing as an application itself, which is extremely important when you think about serving things at production scale.
And those metrics actually looks very interesting. So it shows like there were about 310,000 calls which were made, and how about 300,000 were processed with a success rate of 99%. So that's what the agility and scalability I was talking about. You can actually track all the metrics about your API through this console, and also you can actually deploy multiple APIs endpoints so that you can have some kind of high availability or load balancing, all that kind of stuff. So that's pretty cool. Thank you, Justin.
Yeah, thanks.
If you would like to go into a little bit more demos, or you want to know a little bit more about the products, please feel free to stop at the Cloudera and Fast Forward Labs booth, which is on the first floor.
Yep, we'll be there.
Thank you.
So thank you for the talk.